Block 1. The Ocean's Call and Early Ambition. It's 1939 in Tokyo, and a young woman named Katsuko Saruhashi is staring out a window, not at the city, but at the rain. While others see a simple downpour, she sees a grand, interconnected system. She's transfixed by a single question that will define her life. How does this water, falling from the sky, make its way through the earth and into the vast, mysterious ocean? This wasn't idle curiosity. It was the birth of a scientific obsession in a time and place that had little room for female scientists. Japan was on the brink of a devastating war, and the established social order was rigid. A woman's ambition was expected to be domestic, her contributions confined to the home. But Saruhashi's mind was already charting courses across the Pacific. She enrolled in the Imperial Women's College of Science, a rare institution that even offered such a path, graduating in 1943 with a degree in chemistry. Securing a position was the next impossible hurdle. The world of Japanese science was a fortress built by men for men. Yet, she found a crack in the wall, a research position at the Meteorological Research Institute, or MRI. It was a government agency, and her role was anything but glamorous. She was an outlier, a curiosity, in a sea of men who likely saw her presence as temporary. The end of the war in 1945 brought devastation, but also a strange, chaotic kind of opportunity. The old imperial structures were crumbling, and new ideas were filtering in. For Saruhashi, it was a chance to prove her worth beyond doubt. While the nation rebuilt its cities, she was rebuilding the very foundations of geochemistry. She returned to university, working at the MRI by day and pursuing her doctorate at the University of Tokyo by night. The conditions were Spartan. Resources were scarce, equipment was often repurposed or handmade, and the institutional support system that her male colleagues took for granted simply did not exist for her. She had to be twice as meticulous, twice as resourceful, just to be considered half as good. Her initial work focused on the chemistry of seawater, a field then in its infancy. She was meticulous, driven by that childhood question about the journey of water. She began developing techniques to measure the components of seawater with unprecedented accuracy. Her primary focus was on carbonic acid levels, a key factor in understanding the ocean's pH and its ability to absorb gases. A lone woman in a 1940s laboratory, she worked tirelessly, perfecting her methods. This wasn't just academic exercise. She was building a toolbox of techniques that nobody else in the world possessed. She was creating a new language to speak with the ocean, to ask it questions it had never been asked before. Her superiors, like Dr. Yasuo Miyake, began to notice her extraordinary talent and precision. She wasn't just following protocols, she was inventing them. In 1950, she published her first research on the carbonic acid system in ocean water, a paper that would become foundational. But even this success was framed by the pervasive sexism of the era. Recognition was slow, and opportunities for advancement were funneled towards her male peers. She was a woman in a man's lab, in a man's field, in a country grappling with its identity. Every data point she collected, every calculation she verified, was an act of quiet rebellion. She was proving day by day that her mind belonged in the world of rigorous scientific inquiry. She wasn't just studying the ocean, she was fighting for her right to do so. The scientific community was largely unaware of the storm brewing within this quiet, determined chemist. And they were equally unaware of another, far more sinister storm that was gathering on the horizon, an invisible radioactive tempest that would sweep across the very ocean she was studying. Charting courses across the Pacific, her work on carbonic acid had prepared her, unknowingly, for the greatest challenge of her career. The world was about to change, and Katsuko Saruhashi, the woman who wondered about the rain, was the only one with the tools to measure the fallout. But would anyone listen to what she had found? Block 2. Tracking the Invisible. Nuclear fallout, that invisible poison, arrived with a blinding flash on March 1, 1954. The United States detonated a thermonuclear weapon at Bikini Atoll in the Marshall Islands. Codenamed Castle Bravo, the blast was more than twice as powerful as predicted, a 15-megaton explosion that vaporized 3 islands and sent a mushroom cloud of pulverized radioactive coral into the stratosphere. Hundreds of miles downwind, the crew of a Japanese fishing boat, the Daigo Fukuru Yumaru, or Lucky Dragon No. 5, were showered with a fine white ash they called Shino-hai, the ash of death. When they returned to port, sick and burned, Japan was thrown into a panic. The fish they had caught were dangerously radioactive. The U.S. Atomic Energy Commission, or AEC, scrambled to control the narrative, insisting the fallout was localized and the danger contained. They claimed the vastness of the Pacific would dilute any contamination to negligible levels. It was a comforting lie, but a lie nonetheless. Back at the Meteorological Research Institute, Katsuko Saruhashi knew the ocean didn't work that way. The currents she had been studying were powerful, interconnected highways. If radioactive material entered the water at Bikini Atoll, it wouldn't just disappear, it would travel. The Japanese government urgently needed to know the extent of the contamination. How far had it spread? Was their food supply safe? The task fell to the MRI, and specifically to Saruhashi, because she was the only one with the expertise for the job. The challenge was immense. The radioactive isotopes, primarily strontium-90 and cesium-137, were present in minuscule concentrations, like finding a single grain of black sand on an entire beach. Existing methods were too crude, too imprecise to detect them reliably. So, Saruhashi did what she always did. She invented a better way. She developed a new method for measuring radioactivity in seawater with a precision that was 10 times greater than anything that existed before. It was a masterpiece of analytical chemistry, allowing her to track the invisible tracers of nuclear fallout. For months, her lab analyzed hundreds upon hundreds of water samples collected by research vessels across the Pacific. The results were terrifying, and they directly contradicted the official American position. The radioactivity was not contained. Within a year, her data showed that the fallout from Bikini Atoll had been carried eastward by the North Pacific Current, reaching the shores of Japan. Her work proved that the entire western North Pacific was significantly contaminated. This discovery was a geopolitical bombshell. Saruhashi's meticulous data was irrefutable proof that nuclear testing in one part of the world had direct, dangerous consequences for nations thousands of miles away. Her findings fueled the growing international movement to ban atmospheric nuclear testing. But her work didn't stop there. While tracking the movement of radioactive isotopes, she had a profound insight. She realized that the same ocean dynamics that transported fallout also govern the transport of other substances, including carbon dioxide. This led to her most famous contribution, the Saruhashi Cycle. She created the first ever model to quantify how CO2 moves between the atmosphere and the ocean. She demonstrated how seawater's temperature, pH, and carbonate chemistry dictate its ability to absorb the gas, a foundational concept in our modern understanding of climate change and the ocean's role as a critical carbon sink. The Saruhashi Cycle model was revolutionary. She had used the grim reality of nuclear fallout to unlock a fundamental secret of the planet's climate system. Her data was elegant, her models were precise, and her conclusions would reshape both international policy and planetary science. But in the deeply hierarchical, male-dominated scientific world of the 1950s, was a world-changing discovery enough when it came from a woman who was still seen as an outsider in her own lab? Block 3. Science over Stereotypes. A lasting legacy. That question, was her discovery enough, was answered not in a scientific journal, but with a condescending request that became a symbol of her entire struggle. As her international reputation grew, Saruhashi was part of a delegation of Japanese scientists working with international counterparts. During a critical meeting, a senior male colleague, seeing a room full of men and one woman, turned to her. He didn't ask for her expert opinion on geochemistry or her analysis of the latest data. He asked her to pour the tea. This wasn't just a thoughtless comment, it was the distilled essence of the systemic sexism she faced every single day. It was a clear message. No matter how brilliant her mind, no matter how groundbreaking her research, her primary role in their eyes was still a domestic one. Her response was not one of angry outburst, but of powerful, quiet defiance. She refused. She stated that she was there as a scientist, not a hostess, and that if they wanted tea, they could get it themselves. This single act of refusal was as significant as any of her scientific papers. It was a declaration that she would not be confined to the role society had assigned her. She was there to analyze the world, not to serve the men who were doing so. This resilience defined the rest of her career. She refused to be sidelined or silenced. She continued to produce exceptional work, becoming the first woman elected to the Science Council of Japan in 1980. In 1981, she became the first woman to win the prestigious Miyake Prize for geochemistry. She had broken through the glass ceiling, and her first priority was to ensure other women could follow. She knew that her personal success was not enough. The system itself had to change. She took the prize money she had won, added her own savings, and established the Saruhashi Prize. This wasn't just an award. It was a revolutionary act of institutional change. Establishment of the Saruhashi Prize was created specifically to honor and provide vital research funding to promising female scientists in Japan. She knew firsthand that talent was not enough. Women needed resources, recognition, and a network of support to overcome the immense barriers they faced. The prize became a beacon, annually highlighting the incredible contributions of women in STEM and creating a community of scholars who could lift each other up. Her legacy, therefore, is profoundly dual. Scientifically, her work laid the groundwork for our understanding of nuclear fallout, ocean circulation, and the global carbon cycle, fields that are more critical today than ever before. Her precise measurements and elegant models are woven into the fabric of modern oceanography and climate science. But her social legacy is just as powerful. She was a quiet revolutionary who fought not with slogans, but with irrefutable data and unwavering dignity. She faced down the condescension of an entire generation of male scientists and proved that a woman's place was wherever her intellect could take her. She didn't just open a door for women in science, she built a new entrance and handed the key to the generations that followed. Katsuko Saruhashi didn't just measure the chemistry of the oceans, she fundamentally changed the chemistry of the scientific community itself. A blueprint for defiance. Her life is a testament that the most powerful currents are not in the water, but in the unwavering resolve of a mind that refuses to be ignored, a voice that refuses to be silenced, and a scientist who, when told to pour tea, chose instead to change the world.